This is Scholar Strife doing some Algebra 2, analyzing polynomial graphs. So what do we know about this function here? X plus 2 times the quantity x minus 1 squared. Well, we know its degree is 3 because if we FOILed it all out, or expanded it all out, x minus 1, we'll have x times x times x, which is x cubed. This is a new concept that I haven't taught in my class yet. Turning points. That is 2 because that is just the degree minus 1. So in order to figure out the turning points, you just take the degree and then minus 1. And the leading coefficient is going to be 1. Because we don't have, it's just x times x times x. So our first number is going to be x cubed, so the number in front of that has to be 1. Our end behavior, so we have an odd degree, that's 3. And then our leading coefficient is positive. Sorry for the handwriting. So that means as x goes to the left, or negative infinity, our y value, our graph, goes down to negative infinity. As x goes to the right, or positive infinity, our graph will also go up to infinity. And then the zeros. So if we set our function equal to 0, we'll get x equals -2, x equals 1, and x equals 1. So 1 is being done twice. Okay. So behavior near the zeros. So at x equals 1, so this is from last section, we have a multiplicity of 2. That means x equals 1 happened twice. So what that means is that the function at x equals 1 turns but does not cross the x-axis. So that's our tangent. And then at x equals -2, since our multiplicity is 1, it just crosses the x-axis. What's up with my no? Crosses x-axis. Okay. And I'll go over all this once we start graphing. Our y-intercept. So this is when we set x equal to 0. Y equals 0 plus 2, 0 minus 1, 0 minus 1. So that'll be y equals 2 times -1 times -1. So our y-intercept is at 0, 2. Okay. Now we're going to make a table. So x and y. Okay. If I plug -3 into the equation, I'll get -16. If I plug in -2, I'll get 0. If I plug in -1, I'll get 4. If I plug in 0, I get 2. 2 and 4. 3 and 20. Oops, I forgot 1. 1 goes to 0. So let me rewrite this. So 1 went to 0, 2 went to 4, 3 went to 20. There we go. So remember our zeros are -2 and 1. Okay. Okay. So let's plot our points. So -3, comma, -16. Let's just say that's all the way down here. And then -2, 0. And then we have -1, comma, 4. And then we have 0, comma, 2. And then 1, comma, 0, 2, 4, and 320. So we're going to look at like this. Okay. So do we know where the graph turns? Yes, we do. Well, actually, it's an estimate. It turns at x equals 1, or x equals -1. Sorry. So notice how the graph turns at x equals -1, and then it turns at x equals +1. So that's just an estimate based on what we have for our graph. And then our local minimum, so we look at the bumps there. So we have an upper bump and a lower bump. The minimum is our local minimum is the lower bump. So that's at that's at 1, 0. And then our local maximum is this upper bump. So that's at 1, comma, 4. Or -1, comma, 4. Okay, so let's review this graph once again. So our zeros are at -2 and 1. So here and here. So because our 1 appears twice, notice how the graph touches 0 at x equals 1 and then it goes back up. So it's tangent. Versus at x equals -2, it just goes straight through the x-axis. Okay? And then our behavior matches. As x goes to the right, we go to positive infinity. As x goes to the left, we go to negative infinity. All right. Here we go. So if you made a rectangular box on a cardboard before, this might be a lot easier to understand. But here we go. Word problem. Example, you're making an open rectangular box out of a 16-inch by 20-inch piece of cardboard. Okay. The box will be formed by cutting out the corners of the rectangles and folding up the sides. You want the box to have the greatest volume possible. So write an expression for the volume of the box. So first thing you gotta do, always draw a picture. It helps. So I got a box. Or right now a piece of cardboard. So here's our piece of cardboard. We have 16 by 20. And then all our corners here are going to be cut out, and then we're going to fold. And we want to maximize our corners. But we don't know what it is, so that's going to be x and x, 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 x. These are x's. Okay. So after we cut out our squares there, our new length here, 20, is going to be 20 minus 2x because we're cutting out an x from this side and x from this side. And then our new width is going to be 16 minus 2x. Okay? So, volume is length times width times height, if you remember from your geometry. Length, in this case, is 20 minus 2x. Or you could have had width be that. Doesn't matter. But our height is going to be our little squares, which are x. So write a verbal model. So our verbal model is length times width times height. And then we're going to multiply. Woo. So volume equals 4x squared minus 32x minus 40x plus 320 plus times x. So our volume is 4x cubed minus 72x squared plus 320x. Alright, let's keep going. What is the maximum volume of our box? So the maximum volume, we have to graph the function. So we just change this here into y equals. Okay. So we want to consider the interval 0 to 8, just because if we have an x value less than 0, that doesn't make sense. We can't have a negative height. And then at the same time, if we take 8 feet off or not, what are we doing, 8 feet? 8 inches. So if we take 8 inches, our width will disappear. 16 minus 2x, and if x was 8, then 16 minus 16 would be 0. So the width would be negative if we had gone any further. So, I didn't realize this, but this is going to be a graphing calculator problem. So if you're using a graphing calculator, change your window. So for your x, it's going to be 0 to 8. And then for your y, it would be 0 to 430. So now I'm going to use Desmos because I still haven't found a really good calculator app. But if you're in class, I'll be using the graphing calculator. Here we go. Let's go. Ta-da. Desmos. And then I'm going to make a graph here. So this was 4x cubed minus 7x squared plus 320x. So we're going to zoom out a little bit. And it's more. It's more. It's more. It's more. What's going on here? 4x cubed. Oh, that's why. 72x squared. There we go. So let's zoom in a little bit. So I got a 0 at 0. I got a 8 at 0. And I got a 10 at 0. But that's not what I'm looking for. I'm looking for maximum. So we're going to look at, we're going to scroll up here. And let's zoom in on this area. So remember, our local max is where it reaches, well, reaches what, our upper hump? That. And that point, if it would let me, why won't it let me? Does it not like what I did? There we go. So our hump is right there. Oh, I want to zoom, 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 zoom. Select the graph here. There we go. That point is at 2.945, 420.1. So let's go back to our problem here. So this is our local maximum. It's between 0 and 8. Yes, our maximum value would be infinity, but we got to remember we can't cut out an infinite amount of this box. There's no infinite amount. So our answer is 2.945, 420. So let's go back. All right. So local max, x is around 2.945. And our y value is 420.1, or how much was it? Yeah, 420.1. So max volume is about 420 inches squared, or cubed. Sorry. Volume is in cubic inches, or cubic units. And then how long should the cuts in the cardboard be to maximize the volume? And we said 2.945 inches, or around 3 inches long. And then what are the new dimensions of our box? Let's just use x being around 3 to make it a little bit easier on ourselves. Because if we're actually going to cut it out, we're not going to go 2.95. We might go 2.9, but we're most likely just going to go 3. So length is equal to 20 minus my 2 times 3, which is now 14 inches. My width is going to be 16 minus 2 times 3, which is 10 inches. And then lastly, my height, we chosen to be 3. Alright. Hopefully that helps. Have a good day.